Welcome to Lecture 37. And in this lecture, we'll talk about a new topic called Redundancy in States. And it refers to the states of a synchronous circuit. If you refer back to lectures 26 and 27, you'll see that that was where we did our first design problem with a synchronous circuit. And so let me actually put this up here, lectures 26 and 27. And in those lectures, we were trying to design a synchronous circuit to detect the sequence 0, 1. In other words, if we had in the input X, if we had the sequence 0, 1, then right after that 1 was input, we wanted to have an output of 1 in order to signal that the desired sequence had appeared. But at all other times, the output would be 0. And so after doing the design problem, the circuit that is shown right here was what we arrived at, and we left it at that. And in fact, you will recall that we did then several other designs where we were trying to detect sequences of 2 digits, just like this one. We did 0, 1, and then I think we did another case where we were trying to detect either 0, 0 or 1, 1. But in all the cases that we did, we were trying to look at sequences of length 2. And in each case, now we were looking at the use of different kinds of flip-flops. In some case, like this, we had T flip-flops. In some case, JK flip-flops. In some cases, D flip-flops. But all of these were similar kinds of problems. But there's a situation here that we never did consider before, and which is worth our consideration at this point. It illustrates an interesting issue that can arise with synchronous circuits. And so let's look at this. Look at this in more detail. This was the circuit that we arrived at the end of lecture 27. And if you look at this, there's something sort of interesting. Notice that the output Z only depends on B prime and X. And furthermore, the inputs to this T flip-flop for B only depend on X and B. In other words, what I'm saying here is that the flip-flop for A is really, this is totally independent. There's nothing about A that is affecting the flip-flop for B or the output. So that means that really, in order to detect this sequence, we don't need that flip-flop, this A flip-flop here at all. We could cut out everything in the upper part of this design, and we could have instead a design like this. We could just have T sub B and a clock and B prime and for T sub B we would have X. Well, we have this exclusive OR gate, and what's getting exclusive ORed together are the input X and the output B. And so we would connect the clock here, and then we also take X and we will and X with B and get our output Z. So this circuit alone, which obviously is much simpler than the one above, this circuit would give us the same output as long as we have the same input sequence. And therefore, this would be a much simpler way to achieve this stated goal in this problem. Now, what's going on here? Well, this is referring to a problem called redundancy of states. Now, there is a way using a table to detect a situation when you have redundancy of states, but we're not called to discuss that topic in the syllabus for this course. However, when a situation like this arises where you can see that you can get rid of some of the flip-flops, that's another way of detecting that there must have been redundancy of states. In other words, there must be an easier way of thinking about this problem than what we described originally. Now, what we described originally was not wrong, but we're finding out now that it could have been done more simply. And the simpler way to think about this problem is as follows. Now recall, once again, our goal is to detect the sequence 0, 1. And so instead of having 4 states, you will recall when we looked at this problem before, we had 4 states. 1, 0, 0, 1 was 0, 1, another one was 1, 0, and 1, 1. We called these states S0, S1, S2, and S3. And S0 meant that the last two input values, or last two values of X, were 0 and 0. S1 meant the last two values were 0 and 1, etc. But I'm saying now that when we think about this problem again, and in view of the fact that we know that there must be some redundancy in the way that we originally looked at this problem, we see that really it would be sufficient to describe this problem with just 2 states, S0 and S1. S0 will mean that the last input received was 0, and S1 will indicate that the last input received was 1. Okay, let's last value of X was 0, and this will be last value of X was 1. And now I'd like to show you that if we work with those definitions of states, we will come up with something identical to the circuit we see here. So let's see how that would work. Okay, so we have just 2 states. Here's S0, and here's S1. And S0 means that the last value of X that was received was 0, and S1 means that the last value of X received was 1. Now, suppose we're in S0, which says that the last value of X received was 0. And now we get another input value of X, which is equal to 0. Well, if we get an input of 0, then that means that the last input received then will be 0. So if we get a 0, we want to come back to S0. That's for sure. And now what do we want to output? Well, if we went from S0, which meant that the last input X was 0, and then we got another 0, then that means that the last 2 values of X were 0 and 0, and that's not the desired sequence, so we'll output a 0. On the other hand, if we're in S0 and we get a 1, well, since we get a 1, that means that we should go to S1, because then the last value of X received would be a 1. And not only that, but since the last 2 values would be 0, 1, we would want to output a 1. So if we're in S0 and we get a 0, in S0 and we get a 0, we go back to S0 and output a 0. But if we're in S0 and we get a 1, then we go to S1 and output a 1. And if we're in S1 and we get a 0, we will go to S0. And in that case, the last two values of X would be 1, 0, and that does not match our desired sequence of 0, 1, and so therefore we output a 0. And if we're in S1 and we get a 1, then we stay in S1, and in that case, then the last two inputs were 1, 1, which does not match the desired sequence, and so we would have 0. So this would be our very simple state diagram that we would have in this case. And let's now proceed and see how this is going to work out. So if we have A and B, and then we'll have next value of A and next value of B for X equals 0. Oh, well, actually, notice that actually since we only have two states, we don't need two variables, two state variables, only one will do. So let's call it, to be consistent, rather than calling it A and B, since we're calling in this picture right here, since we have it B, we'll call the one state B, or the one state variable B. Okay, so B, and then B plus for X equals 0 and X equals 1, and Z for X equals 0 and X equals 1. When B is equal to 0, when the state variable B is equal to 0, well, that's the S0 state, and when the state variable B is equal to 1, that's the S1 state. And let's fill this in. So we have found that in filling in now this the entry right here, we have found that if you're in the S0 state and you get a 0, that's this path right here. If you're in the S0 state and you get an input of 0, then you go back to the S0 state and you output a 0. If you're in the S0 state and you get a 1, you go to S1 state, which has a value of 1, and you would output, as we see right here, output a 1. If you are in the S1 state and you get a 0, you'll go back to S0, which is the 0 state, and you output a 0, as we can see right here. If you're in the S1 state and you get an input of 1, you'll come back to S1, which is the 1 state, and you output a 0. So our state table, this is really a transition table, actually. The transition table would look like this. And then if we assume, as we did above, that we want to implement this with a T flip-flop, then let's see how that would go. So we have B and T sub B for X equals 0 and X equals 1, and Z for X equals 0 and X equals 1. And now let's think about T sub B. Okay, if B is 0, if the present B is 0, and the next B is also 0, for a T flip-flop, that means that T must have been 0 since the value of B has stayed the same. On the other hand, if B is 0 and the next value of B is 1, and this is a T flip-flop we're talking about, then it must be the case that t was 1, which will cause the toggle. Likewise here, if b is 1 and the next value of b is 0, since the value of b has toggled, t sub b must be 1. And here, b is 1 and the next value of b is also 1. So the value of the output has not toggled in this case, and therefore t sub b is 0. And of course, we just bring over our information for z. And now we're ready to finish this problem. If we do the Carnot map for t sub b, of course this is so simple here that we'll have t sub b and here we have we can put x here and b up here. So 0, 1, 0, 1, and t sub b, when b is 0 and x is 0, t sub b is 0. When b is 0 and x is 1, t sub b is 1. When b is 1 and x is 0, t sub b is 1. And finally, when both b and x are 1, t sub b is 0. So we would have this Carnot map for t sub b, and clearly we don't have any groupings of any rectangular groupings of 4 one cells, or even any rectangular groupings of 2 one cells. So we only have these groupings of 1 one cell. So we just t sub b will simply equal the sum of these two terms, and this top term I think you can see is x prime b, and that gets ORed with this term, which is x b prime. So t sub b is equal to x exclusive ORed with b. And on the other hand, when we do the Carnot map for z, again we have a very simple situation here. This is only going to be equal to 1. Z is only equal to 1 when b is 0 and x is 1. So b is 0 and x is 1 is right there, and all the other cases z is equal to 0. And so we can immediately identify this as z equals x b prime. And so therefore we conclude that the design is the following. Here's t sub b and the clock. T sub b is x exclusive ORed with b. And z is x ended with b prime. So if we look at the problem with just two states, this is what we arrive at, and you compare that to what we had up here, and you see that it is exactly the same thing. And finally, if you wished, you could go through this, you could go through the analysis procedure, you could propose some input sequence, And in fact, let's just go ahead for the sake of completeness. Let's do that. So, in other words, this is a partial check on our work. Let's determine the output in response to the so I'll say output sequence in response to the input sequence 0, 0, 1, 1, 0. We'll look at this input sequence, and we'll see what the output sequence will be. Now, let's note that the desired output, remember that what we desire to happen here is that we will have an output of Z in all situations except when we see the input sequence 0, 1, as we note right here. So that means that we would want a 0 here and a 0 here, a 1 here, since these last two inputs would be 0, 1, so we would want a 1 there, but a 0 here and a 0 here. So that's what we desire, and now let's find out what the actual Z will be. Okay? Well, in order to do this, we need to do our analysis procedure, just as we have done in the past. This was around lecture 25. So let's look and see what we have. This is like doing the design backwards. So we have T sub B is equal to X exclusive OR with B, and Z is equal to X ANDed with B prime. So now that we have this information, you remembered our first step in the analysis procedure would be the excitation table. And so we'll have B, and then T sub B for X equals 0 and X equals 1, and Z for X equals 0 and X equals 1. Now, by the way, I hope that you can do all of this on your own, and I would strongly encourage you, if you haven't done so already, to stop the video now and try to finish this problem on your own and verify that the actual Z will in fact match the desired Z. So, if we fill in 0 and 1 for B, we should be able now to calculate T sub B and Z. So let's see what happens. Well, if when B is equal to 0, since T sub B is equal to X exclusive OR with B, T sub B will be 0 when X is 0 and 1 when X is 1. But when B is equal to 1, then T sub B will be 1 when X is 0 and 0 when X is 1. And finally, if we fill in the table for Z, we will see that since Z is equal to X ANDed with B prime, whenever X is 0, Z will be 0. So we'll get zeros in this column. And then when X is equal to 1, we'll get a 1 if B is 0 and a 0 if B is 1. So this is what we'll have for the excitation table. And now we can look at the transition table. And again, we'll have B in the leftmost column, and then we'll have B plus, x equals 0, x equals 1, and z, x equals 0, x equals 1. And now let's see what happens. Well, we can go ahead and fill in everything for z, but now in order to fill in the next value of b, we need to remember how the t flip-flop works. So when t is equal to 0, the next value of b is equal to the present value of b. So we're going to get a 0 here. And likewise here, this t is 0. And since the current value of b was 1, the next value of b would also be 1 in that case. But now for the other two cases, in these two cases right here, 1 and 1, remember when t is equal to 1, for a t flip-flop, that means you should toggle the output. So since the output was originally 0, it'll get toggled to 1 in this case. And in this case, since it was originally 1, it'll get toggled to 0 here. So this would be our transition table. And now that we have the transition table, we should be ready to come back up here and finish our problem. Now remember, in everything that we did before, we said that it was okay to assume that there had been previous inputs to the system and they had been 0. And that's important to note now because that will tell us what the initial state of the circuit is. So if there have been initial inputs, if there have been previous inputs and they've all been 0, then that means that the initial state of this is b equals 0. Okay, that's where we're going to start. And again, our x sequence, copying from above, is 0, 0, 1, 1, 0. 0, 0, 1, 1, 0. And now we want to calculate the actual z, and after we've calculated this actual z, we'll see if it matches the desired z. So let's see how this will go. Okay, if we start in b equals 0, so we start up here, and we have an input of x equals 0, then where do we go? We go to 0, so the next value of b will be 0, and we output a 0. Now, go to the next line. If we're in 0, in the state 0, and the input x is equal to 0, then again, we're going to go to 0, and we're going to output a 0. So output is 0. Now, if we're in state 0, b equals 0, and we have an input of 1 this time, as you can see right here, x is equal to 1, then we're going to go to the state 1. So b will be equal to 1, and we will output a 1. Now, if we're in state 1, we'll come down here to the second row. In that state 1, and we have an input of 1, then we will go to state 1 as our next one, so 1, and we will have an output of 0. And then finally, if we're in state 1, as you can see here, and our input x is equal to 0, we will go to 0 as our next state, and we'll output a, as we can see here, a 0. And let's see, I think there's a problem here, but let's check. In this one, yes, I'm afraid we made a mistake here, so let's go over this carefully again. Okay, this one, we were in state 0. So here we're in state 0, and we get a 1. So we go to state 1. This is correct. And in state 0, and you get a 1, you output a 1. So this is correct right here, but now this one, there was an error, as you'll see. If you're in state 1, and you get an input of 1, then you go to 1 here. So you got an input of 1, you go to 1, but you output a 0. So this should be a 0 here. Sorry about that. And so if we look now at the actual output that we will get from this circuit, you see that it matches exactly the desired output. 00100, 00100. So now that doesn't prove that this is correct, but it almost proves it. I mean, it gives you a lot of confidence that what we have done here is indeed correct. So the lesson to take away from all of this is that you sometimes can have a situation where you think you need a certain number of states in order to describe a problem, but it turns out that you can sometimes get by with fewer states than that. And as I said, there's one way to detect this using a table, but that's not part of this course. That's not in the syllabus at the present time. But if you ever see a situation like this, and your final answer where one flip-flop, one or more of your flip-flops that you have is really unnecessary, it can be discarded, then that tells you that you had some unnecessary, or in other words, some redundant states in your formulation. So now that we have seen this example, let's ask ourselves, well, what about let's find another problem where we have where we have four states. Remember, in our simpler case here, we had just two states. Let's try to find another one like the original formulation where we had four states, but there's no redundancy. Can we find something like that? And I believe we can. And so let's do the following. Let's design a circuit to detect. Now we'll be detecting a sequence not of length 2 bits, but of 3 bits. So design a circuit to detect the sequence 0, 1, 0. And what we mean by that is that we want the circuit to output a 1 as soon as it detects that 0, 1, 0 sequence. In other words, just after that last 0 comes in, we want it to output a 1 in that case, but otherwise to always output a 0. So let's see how this would go. Well, in this case, since we're looking for a sequence of length 3, we will indeed want to define our states. Actually, we'll define them just as we did before. Last two inputs were 0, 0. Last two inputs were 0, 1. Last two inputs were 1, 0. And the last two inputs were 1, 1. And now let's see how this would go. And really, I very strongly encourage you to try to do this on your own. So here will be S0. We'll go ahead and put in S1, S2, and S3. Now if we're in S0, which is the state that says the last two inputs have been 0, and we get a 0, then we stay in that state. And in that case, then the last three inputs would be 0, 0, 0, which does not match the desired sequence, and so our output would be 0. On the other hand, if we're in S0 and we get a 1, then that means the last two inputs were 0, 1, which would go here. And in that case, then the last three inputs would be 0, 0, 1, which does not match the desired sequence, and so the output would be 0. Now, what if we're in S1, which means that the last two inputs have been 0, 1? Well, if we're in state S1 and we get a 0, then the last two inputs would be 1, 0. So that's if we get a 0, we would go over here to S2, which would say that the last two inputs have been 1, 0. And now notice also that if that happens, then the last three inputs have been 0, 1, 0, which does match the desired sequence. And so in this case, we would want to output a 1. But if we were in S1 and had an input of 1, then that would say that the last two inputs were 1, 1, so we would go to 3. And in that case, the last three inputs would be 0, 1, 1, which does not match the desired sequence, and so therefore we output a 0. Now, what if we're in S2, which is that the last two inputs were 1, 0? Or if we're in S2 and we get a 0, then the last two inputs would be 0, 0, so we would go up to S0. And what would we output? Well, if we had an input of 0, then the last three inputs would be 1, 0, 0, which does not match the desired sequence, and so we output a 0. On the other hand, if we're in S2 and we get a 1, an input of 1, then that would mean that the last two inputs were 0, 1, so we would go back to S1. This would be 1. And in that case, the last three inputs would be 1, 0, 1, which does not match the desired sequence, and so we output a 0. And now finally, if we're in S3 and we get an input of 0, then that would mean that the last two inputs were 1, 0. So we would go to S2, that's 0. And that does not match the desired sequence. 1, 1, 0 does not match the desired sequence. And therefore, we would output a 0. And finally, if we're in S3 and we get a 1, we go back and again output a 0. And this will be the state graph for this particular problem. So now we can make our state diagram. Now you may be ready to go directly to the transition go to the state table. You may be able to go directly to the transition table, and if so, that's fine, but I'll go ahead and put the state table. So we have S0, S1, S2, and S3, and we'll say next state, X equals 0, X equals 1, and Z, X equals 0, X equals 1. So as you can see now, if we're in S0 and we're in S0 and have an input of 0, we go back to S0 and output 0. So S0, 0. If we're in S0 and we get a 1, we go to S1 and output a 0. S1, 0. If we're in S1 and we have an input of 0, then we go to S2 and output a 1, S2, and 1. But if we're in S1 and we have an input of 1, Then we go to S3 and output a 0. S3, 0. If we're in S2 and have an input of 0, we go to S0 and output a 0. S0, 0. If we're in S2 and we have an input of 1, we go to S1 and output a 0. S1, 0. Finally, if we're in an S3 and we have an input of 0, we go to S2 and output a 0. S2, 0. But if we're in S3 and have an input of 1, we'll go back to S3. That should be 0 over here. For the word. We go back to S3 and output a 0. So here is our here's our state table for this problem. And now let's look at the transition table. And so we will identify S0 with A equals 0 and B equals 0. We'll identify S1 with A equals 0 and B equals 1. Let me make sure it's clear here, we have 4 states. So to have 4 states, we need 2 state variables, A and B. And so we'll just define them in the way that seems pretty natural, that when A and B are both 0, that will correspond to S0. When A is 0 and B is 1, that will correspond to S1. When A is 1 and B is 0, that corresponds to S2. And when A and B are both 1, that will correspond to S3. And then we'll have A plus, B plus for X equals 0, X equals 1, and Z for X equals 0 and X equals 1. And so this would be 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0. Now to go to the excitation table. We need to know, in order to do this, we need to know what kind of stuff flip-flops we're talking about. And let's just keep it simple. Assume A and B are the outputs of D flip-flops. As you know, that will make it nice and simple. So we'll have A and B, and then the D flip-flop for A will have an input D sub A, and the D flip-flop for B will have an input D sub B. Now, I strongly encourage you to stop at this point and to fill in the rest of this excitation table. Okay, so I hope that you had luck filling in the excitation table, but now we'll do it all together to make sure of how this goes. So we recall that for a D flip-flop, the next value of the output is simply equal to D. So since we want the next value of A to be 0, 1, 0, 1 here, then that will be the value of D sub A, 0, 1, 0, 1. And Also, when x is equal to 1, we still have those same values for the next value of a. 0, 1, 0, 1. So 0, 1, 0, 1 here as well. But for the next value of b, which will of course be determined by d sub b, we want it to be 0 in this entire column when x is 0. So 0, 0, 0, 0. And in the entire column where x is 1, we want it to be 1. So 1, 1, 1, 1. And now that we have that excitation table, we're ready now to find d sub a, d sub b, and z as functions of x, a, and b. This will be our goal, and in fact that will lead us to our test. So for problem 37.1, find the minimal sum expression for d sub a as a function of x, a, and b. And then 37.2, find the minimal sum expression for d sub b as a function of x, a, and b. A, B, C, and D. And then finally 37.3 in class. And give me a moment to fill in these choices, and then we will finish this lecture. Okay, so now we'll resume, and you'll see that I've made a slight change. I've also made 37.3 to be one of your questions, and 37.4 will be in class. But let's go over these problems. So based on this excitation table here, you should be able to answer these questions, which are 37.1, find the minimal sum expression for d sub a as a function of x, a, and b. And your choices are, choice A is x prime, a prime, b. Choice B is x. Choice C is a. And choice D is b. And notice that you have exactly those same choices in exactly that same order for question 37.2 and also in question 37.3. The difference is in 37.2, you're asked to find the minimal sum expression for d sub b as a function of x, a, and b. And in 37.3, you're asked to find the minimal sum expression for z as a function of x, a, and b. And I'll go ahead and tell you ahead of time what 37.4 is going to involve, and that is 37.4. In 37.4, you will be given an input sequence, and you'll be asked to find the output sequence that will result. Now remember that what we desire to have, if we look up here at the description of our problem, this is the problem that we're doing. We wanted to output a 1 when we see the input sequence 0, 1, 0, but output 0 at all other times. So keep that in mind, but you know what you're going to have to do to answer 37.4 is basically, you're okay from 37.1, 37.2, and 37.3. You'll be able, since you'll have minimal sum expressions for D sub A, D sub B, and Z, you'll be able to build a circuit. And then to do 37.4, you really have to then analyze that circuit and see if it's working in the desired fashion. So there will be a fair amount of work involved for you to do 37.4, and I would suggest that you go ahead and do that from the beginning, and you'll have your circuit, you'll do the excitation table, then you'll do the transition table, and really as we saw in the case we did above, once you get the transition table, that you can really stop there, because then once you have that transition table and you're told what the beginning state will be, and as usual, we'll assume that there have been previous inputs and they have all been 0. So that means that your initial state will be that 0, 0 state, or S0. So all you need then, once you have the transition table, all you will need is that input sequence, and you'll be able to work through it and figure out the output sequence. So that's what you will have to look forward to for the in-class problem. But that concludes this lecture, and good luck.